current electricity, which is about the Ohm's law mainly we seen, and after that we already seen about the resistance, of which the resistance when connected in the series and parallel we seen. This is called series connection, that is of which R1 resistance, R2 resistance both are connected side by side here. Okay. So that in this case we already derived that the resistance in the series, it finally becomes the equivalent resistance is R1 plus R2, that is. If suppose if you are taking, if R1 is equal to R2 is equal to R, then RS becomes R plus R, which is 2R. If you are taking for the case of two resistance and we got R1 plus R2 which is equal to, we are taking that R, so that we are getting the final resistance R as 2R we are getting. If you are taking two resistance, that is of 2R, if you are taking like that n number of resistance at the same time in the series connection, then it becomes NR. So means if you are taking the resistance here total n, R1, R2, R3 and so on Rn, then the resistance, if all these are connected in series, then we will getting then Rs is equal to R plus R and so on up to n times we are taking. Okay. Then the final resistance it becomes NR. This is the resistance connected in series if n number of resistors at a time we are taking. And in the same way we already discussed, if you are taking any of the two resistance, if they are connected in case of parallel of which R1 and R2, in this case we got Rp is equal to, when connected in parallel, okay, we got that as 1 by Rp is equal to 1 by R1 plus 1 by R2, that is 1 by Rp is equal to 1 by R1 plus 1 by R2, that is. Then 1 by Rp, if you take 1 by Rp is equal to, if you take LCM R1 plus R2, so that we are getting here in the numerator part R1 plus R2, that is. Then resistance when connected in the parallel becomes Rp is equal to R1 R2 by R1 plus R2 we are getting. Which means when two resistance when connected in parallel, the final equivalent resistance we are getting, that is nothing but in the numerator we are having the product of resistance by sum of the resistance here, sum of the resistance, product of the resistance by sum of the resistance we are getting when connected in parallel. As you are taking two resistance here, we got R1 and R2 by R1 plus R2, that is. For suppose just like the previous case, if you are taking total n number of resistors, if you are taking, if all these n resistors if you are connected in parallel, then the final resistance, equivalent resistance becomes like this, as Rp is equal to, here I am taking, let us suppose R1 is equal to R2 is equal to R, that is. Then when connected in parallel, we got Rp is equal to, as it is a product of the resistance, which is, as we are having two are there, R1, R2 by sum of the resistance, which is R1 plus R2, that is. Then R1 into R2, which is R into R by R plus R it becomes, which is of here R into R, R square, and R plus R, that is of 2R, that is. Okay. Then one of the R get cancelled and finally we got R by 2. So which means if you are taking total n number of resistance at the same time, then finally what happens there is, here you will get as it is of R by 2, if two resistance are connected. If R resistance like this, if total n are connected, then finally the equivalent resistance Rp becomes R by n, that is like this. So when connected in series, we got Rs is equal to NR, and if you are connected in case of parallel, Rp is equal to R by n, that is. Then suppose if you are taking these resistance which are connected in the series and which are connected in the parallel, if you want to take the ratio between them, means Rs by Rp, then it becomes, as Rs value is n into R, Rp value it is of R by n, then R get cancelled and finally we are getting n square, which means that finally Rs is equal to n square of Rp, that is like this. We are taking total two resistance here, of which one of the resistance having, let us suppose 10 ohms, another one we are taking, let us suppose 40 ohms. And these two again we are connected to a battery which is of, let us say, 12 volts. And now this again it is connected to another 3 resistance which is of 20 ohms, next one 30 ohms, and another one 60 ohms, that is like this. Like this, if we are having a circuit is there, so that we are having total 5 resistors are present. Here 2 are in parallel, again 3 are in parallel, and these 5 is again passing through any of the battery source here, like 12 volts is given here. For these type of problems, we have to separate the circuit and we have to do our problem there. For example, in the first case, we are having 10 ohms and 40 ohms is there. For this part, if we are taking, first we are taking for this part, okay, means for this, first we are finding the equivalent resistance there. Whereas the two are connected in 10 ohms and 40 ohms, which are connected in parallel, we know that Rp resistance when connected in parallel is equal to, that is of sum of that, which is of 1 by Rp, R1 into R2, which is of 10 into 40 by 10 plus 40, that is, which is of product of the resistance by sum of the resistance, that is. Then you will get 400 by 50, that is, of which Rp value we are getting total 8 ohms. Okay, like this. This is the case if you are taking for the first one when 10 ohms and 40 ohms when both are connected in parallel connection, that is. And in the next case we are having total 3 resistors are connected, again these 3 are also in parallel, that is, for this case. For this case separately if you are taking, again this is the second case circuit, 1 by Rp dash let it be, as again they are in parallel. Now as we are having total 3 resistors are there, means 1 by 20 and 1 by 30 and 1 by 60, that is, like this, 1 by 20, 1 by 30 plus 1 by 60. Then if we take LCM, if 60 is the LCM, then let it be, then 23s and 32s and 1s. This is 1 by Rp dash, that is. Then how much you will get is 1 by Rp dash is equal to 6 by 60, which is of Rp dash is equal to 10 ohms we are getting. Okay. So for the first case of when parallel 2 resistors are in parallel, we are getting 8 ohms. When 3 resistors are connected in parallel, we are getting here 10 ohms. But if you observe here, this parallel connection which is of Rp and the second parallel connection which is of Rp dash, these two again are connected in series. Then when connected in series, Rs is equal to Rp plus Rp dash, like this. Then the total resistance, it becomes, first case is it is of 8 ohms, second case we got 10 ohms, total it becomes 18 ohms, that is. So this is the total resistance of which we are having throughout this circuit. Okay. For suppose if you are taking that into a diagram picture there, then how we will get is like this, like this. For the first case of which for this part, if you are taking, then the circuit becomes, here where we have Rp value which is equal to, we got 8 ohms, and here we are having that battery is there, and for this circuit which is Rp dash, that is, again we are taking one more resistance there, equivalent resistance, of which we got this one as 10 ohms, and now this is the connection. This one is changed like this. And again the second case which is of as Rs is equal to Rp plus Rp dash case if you are taking, then this circuit again it changes to taking all at one resistance, that is, and again we are having which is of Rs this is, and only the battery is connected like this, which is of 12 volts, and here we got Rs 10 plus 8, 18 ohms, that is. So we are making this which are of 5 circuits, 5 resistors of which are in parallel connection there. of which 2 are in parallel separate, 3 are in parallel separate, and these 3 and 2 both are in series. We are making that step by step. Finally, we got the equivalent resistance throughout this 5 resistance here. And if you want to find the current here, how much is the total current passing through that, then we know that as V is equal to IR, then I is equal to V by R, that is. And how much is the voltage we are supplying? It is of 12 volts. And how much is the R given? That is of R is equal to, we got 18, that is. It means 6 by 9, that is. Okay. So, of which we are getting 0. As it is of 6 amperes, 0.6 amperes, that is approximately. Okay. So, like this we are making the circuit into a simple equivalent circuit, and finally we are finding the series connection and parallel connection, and finally we are getting the current here, which is of 0.6 amperes, that is. And in the same way, if you are taking for the case of this parallel connection, of which that Rp value it is given as 3 ohms, that is. As Rp value is given as 3 ohms, then here it becomes, we know that as 1 by Rp is equal to 1 by R1 plus 1 by R2, which is of R1 plus R2 by R1 R2, and Rp then it becomes R1 R2 by R1 plus R2, that is. Okay. This value Rp, it is already given that it is equal to 3 ohms. Okay. Rp is equal to, we already given that is of 3 ohms, that is. And we know that already R1 plus R2 is 16, and R1 R2 we can get from this value. So that if Rp becomes, Rp is equal to R1 R2 by R1 plus R2 value, we already know that as 16 ohms is equal to 3 ohms, that is. Then Rp becomes finally, which is of Rp is equal to, we got R1 R2 by 16, which is equal to 3, then R1 R2 is equal to 16 3 48 ohms, that is. So we got finally 2 values, R1 plus R2 which is 16 ohms, and R1 R2 which is equal to 48 ohms we got. Okay. Then if we take the values of R1 and R2 and R1 R2, directly we can find about that R1 and R2 values. For example, like this. As you have R1 plus R2 is equal to 16 ohms there. Okay. R1 plus R2 is 16 ohms there. From this we can write R2 is equal to 16 minus R1, that is. R2 equal to 16 minus R1. And we also know that their product is 48, that is. Then R1 into R2 is equal to 48 ohms. From this you can write as R1 into R2 value is 16 minus R1, that is, which is equal to 48. Then R1 into 16, 16 R1 minus R1 into R1, R1 square is equal to 48. If you bring that to the other side, then R1 square minus becomes plus, and 16 R1 coming that side becomes minus 16 R1 plus 48 is equal to 0. R1 square minus 16 R1 plus 48 is equal to 0, that is. Then if we are taking the factors for 48, of which we can take 12 fourths, which is of minus 12 R1 minus 4 R1 plus 48 is equal to 0. Then if you take common, then R1 which is R1 minus 12 and minus 4 if you are taking R1 minus 12, that is equal to 0. So finally we got, of which R1 minus 4 if you take common R1 minus 12 is equal to 0. Means for R we are getting total 2 values we are getting, which is R1 minus 4 is equal to 0 and R1 minus 12 is equal to 0, that is, which is of, finally we got R1 minus 4 is equal to 0, which is R1 gives 4 ohms and R1 minus 12 is equal to 0, which is of R1 is equal to 12 ohms. When R1 is equal to 4 ohms, obviously R2 becomes 12 ohms. If R1 is 12 ohms, then R2 becomes 4 ohms. So, the combination we are taking, which is of R1 and R2, this becomes, if one of that is a 12 ohm resistance, the other one is going to be 4 ohms, or if R1 only if it is becoming 4 ohms, then R2 is becoming 12 ohms, that is. Like that, if two resistors, both the cases, the series and parallel connection are given, the equivalent resistance, we can find separately that R1 and R2 values. Now, we will see another model of finding the equivalent resistance when the resistors are connected in parallel or series. Let us suppose in a different model, we will see like this. Here we are assuming a resistance here, total 4 resistance, one like this and another one like this and another one like this. So, that we are having the voltage connection here, let it be, it is in between A and B like this, which is, let us suppose this is 4 ohms, this is 4 ohms, and now we are taking one more like this. Like this, appears to be like a triangle here. Okay. So, 4 ohms, and let us suppose these two again 8 ohms and 8 ohms. And what we need is the equivalent resistance between this A and B. Let us suppose the junction points here, let it be this is C and this is D and this is E and let it be this is F, like this, A, B, C, D, E, F, that is. So, total we are having total 4 resistance are there. In this case, whenever if you are having the difficulty to find out which one is series, which one is in parallel, then how to take is, as you are finding the equivalent resistance between A and B, then let us assume the current is started from the point A. Okay. So, whenever if you are taking about between two different points, if you are finding the equivalent resistance between them, then what we have to take is, let us assume there is a current is passing from the point A, that is, when the current point started from the point A here, now whenever it reaches the point E, it is choosing two different paths, going up there and going towards this direction. So, we already know that before earlier classes we already seen that whenever the current is dividing, only that is possible in case of parallel connection, that is. So, obviously, it is very clear that this 4 ohms resistance which is kept in between E and D and this 4 ohms resistance between E and F, at this junction point of E, as the current is dividing in two different paths, this 4 ohms and this 4 ohms, these two are connected parallel to each other. And in the same way, whenever this 4 ohms is passing here, the current through the 4 ohms, and it passes the same current through 8 ohms, which is very clear that as the same amount of current is passing through both 4 ohms and 8 ohms here, then 4 ohms, 8 ohms, these two are connected in series because the current passing through them is same. And in the same way, if you are taking that current which is of for the ED, now whatever the current which is passing through this ED, the same current actually it passes through between D and C also, which is 8 ohms, that is. So, means here if you observe the current which is coming from E, F to C, okay, and in the same way E, D to C. These two 4 ohms and 8 ohms are in series, these two 4 ohms, 8 ohms are in series connection, that is. And not only that, here in this case, as here the current is dividing this 4 ohms and this 4 ohms, these two are connected in parallel, means I can take the same circuit like this. As it of having 4 ohms and 4 ohms are connected in parallel, now I am assuming the same circuit like this. This is one 4 ohms and this is another 4 ohms we are taking like this, this A. Now, this 4 ohms actually when passes through the 8 ohms, the same current, which means 4 ohms and 8 ohms, these two are connected in series connection, that is. So, this is 4 ohms and this also 4 ohms, and which is like E and D we are taking, which is ED part, and now we are taking the next part which is of 8 ohms, that is, which is in series to that one like this, which is the point C here, and again that 8 ohms is connected to the 4 ohms there. So, again here also we are taking that 8 ohms like this, and here we are having that AB is present. Okay. If the junction points, if you see between A to E, that is of 4 ohms is present in between E and D, that is. So, let us suppose this is nothing but that E and D, and D and C, between D and C only we are having that 8 ohms is present. This 8 ohms is between D and C there, and after that again here we are having that F and E there, of which between E and F, that is of another one we have, which is between E and F up to here. Now, we will see one more last circuit here based on this series and parallel connection, that is. As we seen in the before one, now we are slightly changing that, so that we are taking total 6 resistance here, of which this is one 3 ohms resistance and another 3 ohm resistance and another 3 ohm resistance here, like this, 3 ohms, 3 ohms and 3 ohms. This is 3 ohm resistance, and again it is connected to one more 3 ohm resistance like this. Okay, total 4, and again here we are taking one more 3 ohm resistance at here this point. Okay, and another 3 ohms at here. Now, what we need is between these 2 points A and B, now we are taking this current here, okay, the equivalent resistance for this total 6 resistance we want. Okay. Now, if you observe here again, here the current passes between A to B, always following the same rule. Whenever the current is passing through starting from A to the B, if you are taking, of which we need to find the equivalent resistance between the 2 points A and B. Here the current starts, so that it is moving through 3 ohms. At this junction point, if you observe, at this junction point, actually it is the current is dividing again. One is going up and the one is coming through this 3 ohms. Then if you observe here, whatever the current it is passing through this 3 ohms resistance, the same current actually it passes through this 3 ohms and next to this 3 ohms, and again at this junction point it is meeting with this current, that is. So, means through this point, at this junction point, as the current is divided, this 3 ohm resistance and this 3 ohm resistance, these two are in parallel connection, whereas this 3 ohms, as the same current passes, these two are in series, and again the same current also passes through this 3 ohms also. So, which means this one and this one, these 3 are in series, okay, and to this one it is in parallel. And again these two are combined, again it is passing through the 3 ohms resistance, that is. So, that we can break this circuit, again we can take an equivalent circuit for this like this. As this 3 ohms, these 3 are in series, I am making that as only one circuit, that is, means like this I am taking, which is of RS, that is, which is the 3 ohm resistance series connection part, I am taking that as one only, that is. And the remaining part we have, which is in parallel part, that is, which is of RP, which is equal to 3 ohms resistance we are taking. This is 3 ohms. And again here we are having that AB is there, which is of 3 ohms, and here one more 3 ohms is there, like this. So, this is our junction point. Okay. As there is the junction point is there, as we know that the current passing through that is in 2 different paths, that is why again we are having these 2 are connected in parallel, that is. Then here the RS becomes, as it is of series connection, then RS is equal to R1 plus R2 plus R3, that is. So, RS is equal to R1 plus R2 plus R3, 3 plus 3 plus 3, total it becomes 9 ohms, that is. Okay. Finally, we got a 9 ohm resistance and a 3 ohm resistance, so both are connected parallel to each other. As it is of 9 ohms and 3 ohms are in parallel, then we can find that RP value for 9 ohms and 3 ohms I am finding. Okay. 1 by RP is equal to then 1 by 9 plus 1 by 3, that is, like 1 by R1 plus 1 by R2, that is, of which you will get 3 and 9, which is of 1 plus 3 we will get, of which 1 by Rp is equal to 4 by 9, of which Rp becomes 9 by 4 that is. Okay. So, now we got the Rp value. So, means the same circuit we can take that as like this, of which as 9 and 3 ohms resistance we got 9 by 4. Now, this 3 ohms resistance, now we are taking, of which if you calculate the value for 2 square and again 2.5, 2.25 ohms that is. Now, here in place of this we are taking substituting a parallel one equivalent resistance Rp, and this is 3 ohms, and now we are connected back to the 3 ohms here. Now, we got a simple circuit now between A and B that is. Okay. So, that we are getting A to B, simply the current is passing through the 3 ohms, the same current passes through Rp and the same current passes through 3 ohms here, where that Rp value we got 2.25 ohms that is. Okay. Then all the 3 are in series connection here, then final the equivalent resistance becomes between A to B. Now, we are taking a equivalent resistance that is, of which Rs dash. Okay. That Rs we have to find there, where Rs is equal to, as it is all are in series here, Rs dash is equal to, simply add all the 3 cases, which is of 3 plus 2.25 plus 3. Then total it becomes 8.25 ohms like this. Okay. So, what we done is here is we just taking a circuit of which if you want to find the equivalent resistance between A and B that is, so that whenever if you are taking a junction point here, what happened there is the current passes through here dividing here between 3 ohms and 3 ohms. So, that is why we are assuming these two are in parallel, and the current which is passing through this 3 ohms resistance, again it passes through here the remaining 2 3 ohms resistance. As the same current passes, we are taking that as a series one like this, taking that as Rs that is 3 plus 3 plus 3, because Rs is equal to R1 plus R2 plus R3 we are taking, that is why we got the 9 ohms, and that 3 ohms and this 9 ohms, again these two are in parallel connection. So, that is why we are just replacing this Rs and this part into a one parallel connection that is, which is of 2.25 ohms we got. Now, this 2.25 ohms, this 3 ohms and these 3 ohms, again all the 3 are in series, that is why we are substituting that as A of to B, which is of Rs dash. That final value we got 8.25 ohms that is. Like this, whenever if you want to find the equivalent resistance between any two terminals, what we have to do is, first if you are assuming a current is passing from one terminal to another terminal, the position where at the point where the current is dividing, we are assuming that is taken as the parallel connection here. Whenever the same current is passing through the resistance here, we are taking that as a series connection, and an equivalent circuits if you are taking, then easily we can solve these problems. Now, already we seen about this series and parallel connection. Slowly we are going to the next topic, which is of very important for our next classes as well as for competitive exams, which is about we are seeing the Kirchhoff laws. Okay, Kirchhoff laws we are taking. Very important one. Okay, Kirchhoff mainly gave two important laws that is. The first one we call that as junction law that is. Current law, or it is called junction law that is, and the second one that is called as voltage law or loop law that is, voltage law or loop law that is, loop. Okay, junction law and loop law that is. The first one is about junction law and the second one is about the voltage, which is about the loop law we call that. Okay. Now, first come to the case of junction law here. Then according to this junction law, if you are taking for the case of the currents passing through any of the junction point here, means I am taking here a junction point. Okay. So, at this junction, in case of particularly the closed circuit, if you will see, more junction points will have. At any junction point, according to this Kirchhoff first law, whatever the number of currents coming inside, okay. So, means let us suppose here at this point, I am having the currents I1, another current I2 and another current I3. If these three are coming inside, so that they are going in two different directions, let it be this is I4 and let it be this is I5, like this. Okay. So, at this junction point actually if you see 3 currents are incoming there and 2 currents are going outside here. Then according to this junction law, Kirchhoff first law, then the algebraic sum of the currents, okay, see the statement, the algebraic sum of the currents, algebraic sum of currents at the junction point, is 0. Okay. At the junction point if you are taking here, no currents are accumulating here, means no charges are present at this point P. Whatever the incoming currents we have, that currents are leaving here. Okay. So, this is according to the conservation of charge we can say, which is called conservation of charge. Okay. So, then if you apply that law here in this junction law example here, so what I said, the algebraic sum of the currents at the junction point is 0. So, let us suppose our junction point is at here at O. At O if you observe I1, I2, I3 are the 3 currents which are incoming here and I4 and I5 are the currents which are leaving the point here. Then we can take at the junction point at O, whatever the incoming currents, always with the same sign convention, that is always take the incoming currents as positive and the leaving currents as negative here. As the incoming currents in this case we are having total 3 are there, which is I1, I2, I3. Take that as 3 as positive and the leaving currents which are 4 and 5 are there, of which the leaving currents we are taking that as negative here, which is minus I4 minus I5, like this. Then according to this law, the algebraic sum of the currents, now we got the sum of the currents of the junction at the junction point is equal to 0 we are taking, then it is equal to 0. Then from this you can see I1 plus I2 plus I3 is equal to I4 plus I5, like this. Then if you observe whatever the current incoming I1 plus I2 plus I3, that is equal to the outgoing current which is I4 plus I5, where the current I is nothing but the rate of flow of charge we are taking, means whatever the charge it is incoming at the junction point O, the same amount of current is leaving, means the number of charges incoming is equal to the number of charges outgoing here, which is nothing but the conservation of charge only here. No charge is created and no charge is destroyed, no accumulation of charges here. Okay. Always here what happened there is all are coming to the junction point O there and they are leaving from that junction point here. This is Kirchhoff's first law. Okay. See the statement there again, the algebraic sum of the currents of the junction point is 0. If you are taking the sum at this point is 0, means no charge is present at the point O. Okay. And the sign how to take that is, as I said, take all the incoming currents as a positive and take all the leaving currents as negative here. As the incoming currents in our example we took I1, I2, I3 are there which are coming and I3 and I4 and I5 they are leaving. So, that is why here I1, I2, I3 we are taking that as positive, whereas I4 and I5 we are taking that as negative. That is why we got I1 plus I2 plus I3 minus I4, I5 is equal to 0. Then I1 plus I2 plus I3 is equal to I4 plus I5. This is called Kirchhoff's first law, that is. Okay. Now, we will see the Kirchhoff second law, that is. This Kirchhoff second law we will call that as voltage law. Okay. It is called voltage law, or it is also called as loop law, whereas loop means it is a closed circuit we are taking. Okay. In case of a closed circuit, voltage law or loop law, that is. Now, according to this voltage law, Kirchhoff's second law, that is, if you are taking the algebraic sum of changes in the potential difference or changes in the voltage, okay, the algebraic sum of changes in the voltage in a closed circuit is 0. See that again, the algebraic sum of the changes in the voltage or the potential difference also you can take This is also called potential difference. So, the algebraic sum of the changes in the voltage in closed circuit is 0. Here actually we know that the potential difference or the voltage is nothing but the work done, okay, the work done on unit charge. The change in the work done means the changes of energies if you are taking, because work done is nothing but equal to the energy that is. That change in the energies are becoming 0 means no energy is missing here, which that is why this voltage law or loop law, it is taken from, it is a consequence of conservation of energy that is. That is a conservation of energy. Okay. So, the algebraic sum of the changes in the voltage or the potential difference in closed circuits is always it is equal to 0. And what do you mean by this algebraic sum of changes in the potential difference? By taking an example, we can see the statement again here. Okay. Now, in this case, for the example, now we are taking a small circuit of which we are having 3 resistance there. This is R1 resistance connected to a potential V1, which is the battery there, or next one we are taking one more which is of V2, again a resistance of R1 and R2, and now another one more resistance is there which is R3. Like this we are taking a small simple circuit. Okay. Then if we are taking the junction points here, let us suppose this is A, B, C, D, E, F, like this. Okay. Now, we are applying this voltage law or which is the loop law. Now, we are applying for this a simple circuit, that is taking an example. Okay. Now, how we will get this one is, whenever if you are taking this Kirchhoff law which is voltage law if you are taking, then always will follow 2 sign conventions here, okay, which is the first one, first sign convention, it is for the case of resistance we are taking, about resistance. As the resistance which opposes the current, if you are going in the direction of current, in the direction of current. So, if you are going in the direction of current, always we have to take its value as negative. Okay. So, in the direction of current, R is negative we have to take. Okay. And if you are in the direction, the opposite direction of current, if you are taking in the opposite direction of current, opposite direction of current, in this case R is taken as positive, because current also, the resistance also opposes the current. Okay. This is the first sign convention we are taking in case of resistance, that is, which is in the direction of current, R value is taken as negative. And if you are going opposite to the direction of current, then we have to take R value as positive, that is. And the second sign convention we are taking, it is for the case of voltage we are taking, in case of voltage. In case of voltage, how to take that is, if you are going in the direction of current, and that too if you are passing from high potential to low potential, high to low, then in this case we have to take that as negative. High to low means you are going from positive terminal to a negative terminal. In this case you have to take that as negative. If you are going from low to high that is, means like this, negative terminal towards a positive terminal, in this case we have to take the difference in potential as positive, that is. Okay. Plus to minus we are taking that as negative, and minus to plus we are taking that as positive, that is. Okay. Now, following these 2 sign conventions, now we are applying the Kirchhoff's second law for the given small circuit, that is. Okay. Now, whenever you are choosing your closed circuit, let us say for example, in this case we are having a closed circuit here, A, B, D, E, A, that is. Okay. In that again we are having 2 small closed circuits are there, which is of AB, CFA and FCDEF is there. Okay. For AB, CFA, that is, means if you are taking starting from A towards B, now C, and coming back to F and finally to the point A, that is. So, AB, CFA, that is we are taking. Now if you are taking the current directions here, in this case if you observe, then here I1 current is coming, let it be, here let us suppose I2 current is coming. This I1 and I2 both are now at this point junction C, both are added following junction law, which is the first one. At this point if you see, I1 is incoming, I2 is incoming, then I1 is plus and I2 also plus, then finally we will get I1 plus I2. I1 plus I2 to the point D, and slowly it is going towards R3 here. And again whenever it passes through this R3, now again it comes here at the junction point F. Again the current I2 is coming back and again I1 is going up here like this. Like this we can get the current from by using this first law, which is of junction law, that is. Now whenever if you come to the case of this loop law, then once you started taking one particular direction, we have to continue in the same direction here. As for the case of 𝗵𝗂𝗃, 𝗵𝗂𝗃, for this now I am taking, this is the direction like this, following a anti-clockwise direction, that is. So means I am starting from A and I am going towards B, that is A to B. So first going from A to B. Whenever I am going from A to B, now here at any of the electric components you take, total two are there. One is the voltage, another one is the resistance, that is. Then while going from A to B, passing through the resistance, I am going in the direction of current. As you are going in the direction of current, according to the first case of sign convention, the resistance we have to take that as negative. The resistance is taken as negative, that is. As the current passing through this R1 is I1, then the potential drop at that point is minus R1, the resistance we are taking, and I1 is the current passes through that. So I1 minus R1. And if you are taking here, that is going from minus to plus in case of this voltage. Following the rule 2 there, which is of the second sign convention for voltage, as you are going from minus to plus, then we have to take that as positive, which is plus V1 we have to take. Okay? Then that is about A to B part. Now come to B to C. B to C, nothing is there. B to C, nothing there. And C to F, again we are having the electronic components are there, C to F. Then whenever if you are going from C towards F, you are going in the opposite direction of the current here. Okay, we are going in the opposite direction of current. As you are going here in the opposite direction of the current, at first we are having the voltage, and that voltage actually we are having positive high to high potential to low potential, that is, means positive to negative. Following the second sign convention, we have to take that V2 as minus, that is, okay, because we are going from high to low, that is. And whenever it come across the resistance here, which is about R2, as you are going against the direction of the current here, against the direction of current, then R2 value becomes plus R2, that is. And the current passes through that is I2, that is, like this, is equal to 0. Okay, then that is about C to F. And finally F to A, again nothing is present. So means whenever I started from A to A, which is of 𝗵𝐶F to FA here, the total resistance potential difference I am getting like this. Then if you add all of this, means minus of first one I1 R1 plus V1 minus V2 plus I2 R2, this is equal to 0. This is our Kirchhoff second law, that is, okay, which is minus I1 R1 plus V1, that is in between A to B, and between C to F again we are having that electric components are present. Then we got minus V2 plus I2 R2, that is, which is of minus I1 R1 plus V1 minus V2 plus I2 R2 is equal to 0. Okay, this is about the first law or second law of Kirchhoff one. And the same thing even you can apply even for the case of next circuit, that is, which is of, let us say for example, for this one if you are applying there, which is for the case of starting from F now, okay, so which is F, C, D, E, F for this loop. again that is also a closed loop, that is, okay. And again if you are going from F to C, then if you are going from F to C, you are in the direction of current, then we have to get that resistance which is coming here, that is taken as a negative here, because we are going in the direction of current. So that's why I2 following the sign convention, which is minus R2 it becomes, and whenever it comes to the case of the voltage here, minus to plus we have. So minus to plus, which is about positive, that is plus V2, okay. Then that is for F to C, that is. Then again if you come to C to D, nothing is there, and if you go to D to E here, then D to E, then in this case we have a resistance is present. Then as you are going in the direction of the current, that resistance become value minus, that is of minus 3, that is minus R3, and the current passes through that is I1 plus I2. These are the three we have, okay. And after that again E to F, nothing is present. Then you have to take the algebraic sum of all these potential difference across the different components here. So if you add all, minus of I2 R2 first case plus V2, and the second case which is of minus R3 of I1 plus I2, this algebraic sum, it is equal to 0 for a closed circuit. This is what given in case of this Kirchhoff second law. Okay, have understood now how to take for the case of Kirchhoff second law here. See, not only for these smaller closed circuits, even in this example we are having one more closed big circuit is there, A to B, B to D, D to E, and E to A. Even for that also separately you can take a circuit. From this you can find the currents there, the voltage there, and the resistance there. Any of that according to the given numerical we can find that, okay. So following mainly two rules, okay. When you are taking the sign convention for the case of the resistance, if you are in the direction of current, take always the resistance value as minus. If you are going opposite to the direction of the current, take always the resistance value as plus, that is. And in the same way in the second case, if you are taking about the voltage, if you are taking about the potential difference, the voltage there, always if you are going from low to high potential, negative terminal to positive terminal, you have to take that as a positive. And when you are going from positive to negative, which is of high potential to low potential, we always have to take that as a negative, that is, okay. So that is about this Kirchhoff second law, which is the voltage law. And if you are applying for the case of these numerical examples, if you want to take by applying this Kirchhoff second law here, let us suppose again we are taking one simple circuit, that is, of which here we are having 3 resistance here, which is having connected to a battery there. Let it be, this is 5 volts, and one more resistance there, and again the connection we are taking with the 12 volts, okay. And again these two are passed through one more resistance here, like this. So total we are having 3 resistance are there, R1, R2, R3. Let it be, this is of 2 ohms, 3 ohms, 4 ohms, like this, okay. Now in this case, if you want to apply our Kirchhoff law here, then if you are taking here the junction points here, let it be, this is A, B, C, D, E, and F, like this, okay. Now for this one, what we want is we have to find the current which is passing through 12 volts battery if you take. Then whenever if you are taking the direction of current, that always decides about this law here, because we are having different junction points are present here. For example, here if you are taking the 12 volts battery and 5 volts battery, both are side by side is present. Here only you have to take a bit careful, of which here 12 volts and 5 volts, which is the high potential, is 12 volts is the high potential and 5 volts is the low potential for this when connected to the positive here, okay. Then in this case what happens there is the current will start from 12 volts we have to take, okay. Let us suppose here that is of, let it be I1 that is. Okay. If it is coming I1, then here at this junction point the current divides. So, let it be here, if total current is I, if it is passing, let us suppose from here it is going I1 and this is going I2 here, like this. Okay. Now, again the current passes here, coming up here and again going inside, like this. Okay. Of is the total current passing through that 12 volts, which is of I is the current, where that I is equal to I1 plus I2, I is equal to I1 plus I2 that is. Okay. I is equal to I1 plus I2, where I is the current which is passing through the 12 volts battery that is. Okay. As we are having again here, we are having total 2 small closed circuits are present, of which we are having this is one closed circuit and this is another closed circuit. And if you are taking for the first loop, which is about A, B, E, F, A that is. For this first closed loop if you are taking, which is of A, B, E, F, A, for this part if you are taking, again for A to B, nothing is there, and B to E if you are coming, B to E if you are coming, then we are having the electronic components are present, which is of one resistance 3 ohms is there and 12 volts is there. And if you observe here, you are passing through in the direction of the current. Here that current is I1 plus I2, which is equal to I that is. As you are passing through that 3 ohms in the direction of current, following the sign convention, the 3 ohms we have to take that as negative that is. So, minus 3. And the current it is passing through that is I, like this. And when come to the case of voltage, here we are going from low potential to high potential, minus to plus, then it becomes plus 12 that is. Okay. So, I minus 3 plus 12 that is between B and E, no other components are present. And again if you go to E to F, nothing is there, and between F to A, again we are having that F to A here. Then in that case we have, while you are going from F to A, as you are going in the direction of current here, plus to minus, which is of a 5 volts battery is there, so that voltage positive to negative, which is a high to low potential, we have to take that as minus that is minus 5. And whenever you are going to that 2 ohms resistance here, that resistance actually we are taking in the direction of the current. So, that is why the resistance we have to take that as minus. So, that is of minus 2, and the current here it is flowing here, which is of I1 is coming inside. So, I1 of minus 2 that is. This is up to between F to A that is. So, finally what we got is for this minus 3I plus 12 minus 5 minus 2I1. This algebraic sum is equal to 0. That is our first circuit, which is of A, B, E, F, A. So, we can write from the closed loop of A, B, E, F, A, we got minus 3I plus 12 minus 5, which is of 7 minus 2I 1 is equal to 0. Finally, we got this one. Now, come to the second closed loop, of which now we are taking between B, C, D, E, B that is, which is of B, C, D, E and B that is. Second closed loop we are taking. When you are starting from B to C here, as we are going opposite to the direction of current, B to C, no electric components are present. So, no problem to that for BC part. But while going from C to D, here we are having a resistance is present, of which we have to take that as we are going opposite to the direction of current. At that resistance, we have to take that as minus that is. As we are going against to that, as it is a resistance is present, we have to take that as a plus that is, which is of plus 4. And the current passing through that is I2 is the current passing there, as we are going opposite to the direction of current. And again if we come to the case of D to E, nothing is there, and between E to B, again we are having the components are present between E to B. When come to the case of E to B here, now as we are going from E to B, we are going opposite to the direction of current. and here we are having a voltage is present. According to the sign convention here, we have to take, as we are going from high potential to low potential, which is of plus to minus, we have to take minus 12. And if you are going opposite to the direction of current, then that 3 ohm resistance, we have to take that as plus, that is. And the current passing through that is actually I1 plus I2, that is. So, plus 3 of I1 plus I2 we are taking. Okay? Only these two components are present here. Okay? So, finally we got for this BCDEB, we got 4 I2 minus 12 plus 3 of I1 plus I2. This is the equation we got. That is our second equation. Then if you are taking that equation here, of which 4 I2 minus 12 plus 3 of I1 plus I2 is equal to 0. This is the second equation we got. Then if you simplify that equation here, of which you will get 4 of I2 minus 12 plus 3 I1 plus 3 I2 is equal to 0. Whereas actually if you want, you can take this I1 plus I2 is equal to 1, that is of I, that is. Okay, this one. Actually this I1 plus I2 value is I, because I1 plus I2 is equal to I, that is. Then we got 4 I2 minus 12 plus 3 I is equal to 0. This is the second equation we got. Now come to the third case, which is the complete circuit you are taking, which is of A to C, C to D, D to F and F to A if you are taking. Then A, C, D, F and A. For this bigger one, if you are taking A to C, no components are present, but C to D, we are passing against the current, of which resistance becomes minus 4, that is, and the current passing through that, which is of here, the current passing through that is I2, so minus 4 I2, and between here D to F, no components are present, but if you are going from F to A, again we are having that, of which 5 volts is there, which is taken from high potential to low potential, plus to minus, which is minus 5 we have, and against the resistance, we are going in the direction of resistance here, then in the direction of current if you are taking, the resistance becomes minus. In that too, the current passing through that is I1, that is equal to 0. So finally we got minus 4 I2 minus 2 I1 minus 5 is equal to 0. This is the third equation, this is the second equation and this is the first equation. So from the 3 circuits, totally we got 3 closed circuit, 3 equations we got, and if you solve these 3 equations, now easily we can find out I1 and I2 values here.